take it away.
All right. Are we all set up on Zoom in terms of
think
listening
so.
and watching? Great. Hi, everybody. Yes.
Before you start, maybe you want to hide the view because I think this are pushed to YouTube.
Oh, no, it doesn't. It will, the recording doesn't have that.
Oh, it doesn't have it? Great.
No.
All right. We're good?
Yep.
All right. We are good. So hi, everybody. I'm Frank Donnelly. I'm the head of GIS and data services at the Brown University Library. So I work within a little center called CLEAR, which has a little data services hub. And essentially, I help folks on campus who are interested in doing basically geospatial and demographic research. I help a lot of folks learn how to use and navigate GIS software, which is a collection of software data that you can use for doing geographic analysis. But as it turns out, you don't necessarily have to use GIS software. So if you are scripting and coding with Python, you can actually do a lot of geospatial operations and mapping right in Python. So that's essentially what we'll talk about today. I'll give you a little bit of an introduction with geospatial Python with GeoPandas. Two parts to this. First, since this is a data science workshop, I'm assuming that most folks have a little bit of familiarity already with like scripting and coding. But secondly, on the other hand, I'm going to assume that folks maybe don't have experience working with like geospatial data or GIS per se. So what I'd like to do first is I'll give you a little bit of an overview to GIS. And then I have a notebook that I've written. We'll hop into the notebook, see how Geospatial Pandas works, and then pop back and forth a little bit as we like cover different topics. Sound good? So when we're talking about, let me get this bar out of the way. We're talking about GIS. So geographic information systems are a set of software packages and applications for working with geospatial data. And when we use this software, geographic features are represented by individual files or layers that you can add to the software to overlay and make maps. So geospatial data files are not maps in and of themselves, but they're the raw materials that you can use to basically make maps. So for example, I can have a file that has the counties of Rhode Island and another file with the public libraries in Rhode Island. And I'm able to take those two separate files and then bring them into a GIS package and overlay them in order to make maps. And the reason that that works is because these files are not just simple drawings that somebody created in a graphic design package. All GIS files, all GIS data is geo-referenced, which means it's been drawn to a specific map projection and scale, and it is tied to an actual physical location on the Earth. So that when I'm mousing over like an image of Hawaii in GIS, I'm going to see the longitude and latitude coordinates for all of the places that I'm hovering over. So all of these GIS files are geo-referenced and attached to specific spots on the Earth. And since these systems are all standardized, this is what allows us to basically share data with one another. So that if, we've all looked at maps from time to time, right? There are many different map projections, but basically all of these files are in one of these systems. And if you have a data file and I have a file and they're in the same system, we can overlay them on top of one another and use them to do analysis. But if they're in a different system, well, then we can use the library within the GIS that has all of the systems in it and convert layers from one system to the other. There are many systems because there are many different ways of representing the Earth, and there are different reasons why you'd want to use one system versus another. And we'll talk about that a little bit. But then if you're working with GIS software, this is a screenshot of QGIS, which is a popular free and open source package. If you're using this software, it basically acts as an interface or a window for viewing and manipulating these different files so that I could have a point file of bus stops, a line file of bus routes, a polygon or area file of cities and towns in Rhode Island, and then maybe a gridded raster layer that shows me the open street map. I can basically overlay all of these in the package. I can change the symbolization and use them to make maps, and then have access to a wide variety of tools that I can use to do, different kinds of spatial queries or geoprocessing sort of operations. And the data is just out there, like on the internet. So you can just search for it. This is an example of RIGIS. This is the state of Rhode Island's GIS repository. So if you wanted cities and towns, streets, aerial photographs, in some cases like tax parcels, hospital districts, a lot of layers that are distinct to Rhode Island. You can go do a search, download one of these files, and then you can use them either in GIS or with Python. And governments are a primary producer of GIS data. Every level of government is going to produce data that's basically of interest to that level of government. So within the federal government, there's the Census Bureau and the US Geological Survey, and then a lot of other agencies that are producing specialized data. At the state level, every single state is going to have its own GIS repository of data. And then also large cities and counties as well will have repositories. Beyond the government, there are also a lot of nonprofit projects out there, the OpenStreetMap, Natural Earth. So a lot of different places where you can go and basically get geospatial data. So these are basically files that are mappable and ready to go. And when we're talking about representing geospatial data digitally, there are a couple of ways that we can do this. You can think of this as being, there are two different families of formats. The first format, and the one that we're really going to talk about today, is the vector format. In a vector format, you have files that consist of discrete objects that are defined by coordinates. So you can have points, lines, or polygons. And the way that these files are constructed is essentially they are long strings of coordinates that are basically encoded to a specific standard, so that when you open it in a GIS package, it's basically able to take all of those coordinates and then display them as point, line, or area geometry. If you ever worked with, for example, a GeoJSON file, that's an example really of a vector file. It's basically coordinate based. Other formats, like if we went into one of those GIS repositories, there's an old legacy format called a shapefile, which is very common. But basically, it's really the same thing. So we're talking about discrete features that are defined by coordinates. What makes the vector files additionally special is that not only do they exist visually, but there's also a record for them in an attribute table. So GIS basically operates very similar to like a relational database, where each of your features is a record, and then you have columns of attributes. And anything that appears in that attribute table, you can basically manipulate or display that on the map. So if I have a shape file of the 50 states, automatically attached to that is an attribute table, one record for every state. And then if I have columns of the names of the states, then I can use those as labels on the map. Or if I have any numeric data, I can use that as the basis for creating a shaded area map. So any kind of geospatial vector file that we're going to work with is basically going to have these attributes associated with it in a table. And then what makes that also extra neat is that using relational database kinds of techniques, you can basically take plain old tabular data, add it to the software, and join it to the shape files or to the vector data so that you can map that data. So for example, if I have a shape file of the 50 states, and then I go to the Census Bureau and I download just an Excel file or a CSV data table, but each of those records is also for the 50 states, I can bring the table and the shape file together, and using a column that they share in common that has a unique identifier, I can do a table join. And then everything that was in that boring table is now part of the spatial file, and I can basically map it and analyze it. So where does Python come into this? So if you use Python, there's a module called Pandas, which is very popular in data science. The number one thing that Pandas gives us is this gridded data structure called a data frame, right? So in Python, like the regular structures are things like lists or dictionaries, but if we use Pandas, then we have this special data frame structure. We have an actual table that we can identify rows and columns, and then we can do specific things on those columns. And just like in a relational database, the columns are typed. So you can have text columns, different numeric columns, special date columns for recording date and time, and etc. And then this other module, what this brings into the mix, GeoPandas, is basically a spatially enabled data frame. So imagine that you have a special column for holding geometry. So you have your records of all your places, you have all of your other regular columns, but you get this special geometry column which holds all of the geometry for each of those areas. It could be a point or line or an area. And there's basically a specification that's set by the Open Geospatial Consortium, which defines basically how geometry should be encoded in different spatial data sets. So with GeoPandas, we're basically able to store this geospatial data in a column that's typed just for geometry. And then, like any other column now, there are also a wide variety of functions that have been designed to operate on all of the geometry that's stored in this column. So similarly, working in this kind of relational concept where we have these data frames, we can join them together. But if we have any data that's spatial, we can load spatial data like a shapefile or a GeoJSON file into GeoPandas into a geodata frame like this. And we'll do some examples of this in the notebook that I've created. Yes, Paul.
Is the type of this compatible with what you get on PostGIS?
Yes, basically the same kind of geometry types. They're defined by the Open Geospatial Consortium. So point, line, and polygon, and then a multi-version of each one of those as well. And they're kind of encoded the same way. Yep. And we're going to work primarily with vector-based data in the geodata frames today, but just for the sake of completeness, I should also mention that within GIS, there's another way of basically representing geospatial data digitally, and that's the raster format. In a raster, you basically have a continuous surface that's divided up into grid cells of equal size, and each cell has a numeric value associated with it that tells you something about that cell. So common things would be aerial photographs, satellite imagery, data that's been derived from imagery, like this land use land coverage layer where every grid cell represents a land use, or even like old school paper maps that have been scanned and georeferenced. The grid cell would just be the color on that map, which might denote something that's interesting. The formats are things we would recognize. These are basically just digital pictures, but they're not just pictures. These are also georeferenced, so that if we added a raster file to a map, it basically is attached to a specific spot of the Earth and it's warped with a map projection. So you can work with raster files in Python, just not within GeoPandas. GeoPandas is really a vector-based module. There's another module called Rasterio that you can use to work with rasters in Python. So I'm not going to mention that today, but just for the sake of completeness, I wanted to mention that here. So let's take a look at what GeoPandas looks like and how it works. So I've created basically a little tutorial in a notebook, and we can basically just search there and go to it. So this is the URL up here. I'm going to click on that. I'll post it in the chat so that the Zoom folks out there in Zoom land have easy access to it. There it is.
Also the feature actions.
Oh, I'm sorry about that, of course. I should pause right now. Does anyone have any questions before we go into like the hands-on tutorial portion? I know it was kind of a whirlwind tour of geospatial data. If not, what you can do is basically do a search for like Brown University Library, basic GeoPandas example, and basically make your way to this notebook. Or, you can also, this is the URL up here, it's in the library's GitHub instance. And in this notebook, or in this repository, I should say, what we're looking for is the actual notebook, which is just an IPython file called GeoPandas example. I'll open that up. And what we'll do is that Ellen has given me some magic code that will allow us to basically click on this in the repository and basically copy it over into Google Colabs. And then we'll basically clone this repository within Google Colabs so that you can kind of quickly get up to speed with using it. So if you've managed to get to the basic GeoPandas example and you're in the notebook, at the top here, there is a heading for Brown University Colab users. There's a link here that that you should click, and that'll basically bring us over into Google Colabs, your Brown account. And then one thing that we'll need to do in order to run this in Colabs, we'll basically clone the Jupyter notebook that I have in the GitHub repo. by just coming down here to the first cell and clicking this and say yes. And that'll basically now copy that whole repository in here. And if I hit the little folder, then I should see basically all the files that were in the repo or in this temporary folder. I'll just pause for like a minute and make sure that everybody was able to navigate your way basically from here. And then basically opening it up in Colab and then basically running this first cell to copy the repository. Also a good opportunity to eat more pizza. Is everybody who wants to follow along okay with getting set up? You were able to get to this point. I see thumbs up. Every folks out there in Zoom land are good. All right. So of course, here at the top, we're going to have to import some modules that we're going to use. So we have a few. We're going to bring pandas in because we need that. GeoPandas is essentially what we're talking about. And then there's a special module called Shapely, which is associated with GeoPandas. It's something that you would use in instances where you have to create your own geometry. And there's an example of that that we'll take a look at. And then also we'll bring in matplotlib because we'll want to plot our maps so we can see what they look like. So let me import the modules. There we go. And then down here, if I have a shapefile, so let's say, as I mentioned, you can go out on the internet and download shapefiles from many different repositories. I'm going to read this shapefile in from, it's basically the counties of Rhode Island. It's going to draw this from an input folder. If I just open up the input folder, I can show you. Shapefiles are old and funky, even though that's a singular sounding name. The shapefile actually consists of multiple pieces. You actually need all those pieces to be together if you're going to use it. But basically, the process of reading a shapefile into a geodata frame is actually pretty straightforward. So first I say, I'm going to create the path. I always use the OS path join module. Always a good idea to use this instead of hard coding links so that your links, this program will essentially be cross-platform if you were to run it on a different operating system.
In chat.
Yes.
What is the percent matplotlib inline doing here?
What is the percent matplotlib inline doing here? This was just some funky thing in Jupyter notebooks sometimes that in order to basically just show the plot inside the notebook, you have to add that little comment at the top. Otherwise, it will like create it, but not necessarily display it or not display it in the way that you expect. So that's just kind of a thing that basically I copy and paste that over from most notebooks that I work with. So let's read in the shapefile. Let me hit this play button here. So we're basically building the path to where the file is stored. This is the function GDP read file, which is basically loading this into a GeoPandas data frame, a geodata frame. And now let's take a look at the records. So these are the attribute data that was associated with that shapefile. But all the way here on the right, if I move this over here, you can see that there is a special geometry column that holds all of the geometry for the shapes. Looks like we have a multi-polygon and then a number of individual polygons. You're like, oh, okay, so what? To see if this worked, if we come down here to the next step, we can actually plot this. And now it's showing us this is what that shapefile looks like using the geometry in the column. So there are all of our counties. And again, in this case, the plot function we're using, this is just a general pandas or GeoPandas plot function for just quickly visualizing stuff without too much fuss. That's really all there is to it for just getting a shapefile or a GeoJSON file in here. Also in that folder, though, I have a CSV file, which is just not a spatial file, it's just a regular CSV file, but it has some coordinate data in it. If I want to take those coordinates and plot them, I can do that with a few extra steps. I'll run this little piece here so we can see what this looks like. So here I have a CSV file that just has a bunch of test records in it for basic places. And then there are some columns that have longitude and latitude. If you have longitude and latitude in a table, that's not geometry. Those are just numbers that are stored like any other numbers in a column. But I can use GeoPandas to basically use those numbers and build geometry out of them. So if we take a look here, I basically read in the point file, and this business is just the basic Pandas stuff for reading in a CSV. So I'm reading in a point file, I'm specifying a unique identifying column. And then if you're ever working with census data will come with different geo identifiers. It's always a good idea to declare those as strings so that you don't lose the leading zeros that are part of the identifiers. And then the process for building geometry, we just have, kind of this nested function here where we're going to create a geodata frame. And that geodata frame, we're going to build it from the point frame that we just loaded in. And we're going to say that the geometry is going to be equal to, and we're going to add another function. This function points from XY. We'll take your longitude, which is your X coordinate, and your latitude, which is your Y coordinate, and it will basically build geometry out of it. And that's basically what we're getting in this last column here. So beyond just having these coordinates, now we have real geometry. And this function here basically points from XY. You can use that for building geometry if you just have coordinates in a CSV file. Another little wrinkle, though, is that when we're plotting coordinates, we have to say what system the coordinates are in. So it's kind of like if I told you it's 20 degrees outside, you would need to know, is it in Celsius or Fahrenheit? Coordinates are not just absolute numbers, but they're part of a system. And here, the CRS is the coordinate reference system. And what I'm doing here is I'm passing in a specific code that says this is the system that these coordinates are in. In your life, when you are plotting coordinates, chances are the system that you'll be using most of the time is probably this one. So I've just highlighted it here. So every system has a unique number that identifies it. So 4326, that is the identifier for the WGS84 coordinate system. This is the basic longitude and latitude system that GPS uses. And if you download coordinates from most places in the world, if they are modern, chances are that will be the system that they're in. And then when you load data in, you would just define this as the CRS. In my case, though, I didn't do that. I used this other thing. I said the code is 4269. This is a system that the US government uses for most of the coordinate data it publishes. So when I downloaded this coordinate data, I knew where it was coming from, and there was metadata that told me this is the system that it uses. I also know that, since it's US federal data, that it's probably using 4269, which is the system NAV83. I know this is probably the biggest hurdle for people to jump over the first time if you're new to geospatial stuff. We'll talk about that more in just a little bit. Just so you can see, though, let's go ahead and plot the points. So after I loaded in that CSV, now I have geometry. I can plot it here, but the plot thickens. One thing you should notice is that if I compare this to my county file here, the labels on the axes are very different. Up here, I have like these really large numbers that I'm not really sure what they are. And if we go down here to the points, these are smaller numbers that to me look like longitude and latitude. So the fact that we have different looking labels on this axis is a clue that we're dealing with two files that are in two different reference systems. How do we figure out what reference system something is in? Well, we can come down here and there are basically some methods and functions for doing that. So if we take our geodata frame for the counties and say .crs, that will tell me the coordinate system that the county file is in. It tells me that it's in something called NAD 83 Rhode Island feet US, that it's a projected coordinate reference system, and then it gives me a little unique identifying code for that system. It's also helpful. It tells me kind of, these are the areas where you would use this system. Basically, this is a system for Rhode Island and really not for any place else. I can also come down here and with this total bounds method, this will print out the coordinates for the bounding box. So if I was to draw the minimum rectangle around all of my points, what would the basically limit coordinates be? And here, this is helpful for just seeing that, oh, these are just really big numbers. What's going on? Well, let's take a look at the points. If I get the coordinate reference system for the points, it tells me it's in something called NAD83, which is a geographic coordinate system. And this is something that's used basically throughout the entire, all of North America. And if I print the bounds for it, we get much smaller numbers. And if you're a geographer and environmental scientist, you might recognize that these small numbers look like longitude and latitude. So we have these two files that are in different reference systems. How do we transform files from one system to another? Basically just with this little function. If I take the points and I say to CRS, I just have to provide it with the system that I want to put the coordinates in. So I'm going to take the points and put them in the same system as the counties. And then I'm just going to replace the geometry in place so that I don't have to create another frame. And if I do that and return the coordinates, now this geodata frame is in the same system just by running this little conversion. And if I print the bounds for the points now look similar to the bounds of the counties. And now that they're in the same system, I can basically plot them on top of one another. So if I go down here and say I'm going to create a base map where I'm going to plot the counties, and then on top of that, I'm going to plot the points on the same figure. There we have it. The big numbers in this case are a grid that's in feet, because that's what the state plane system uses.
What does the red dot outside of the bounds?
That was on purpose. That's in Connecticut. Because this was test data that I created, and I wanted to make sure what would happen if we plotted something that fell outside of the bounds. Yes?
What determines like the points themselves? Like a representative point for each icon. What is it like? Really?
So the question is, what determines what these points are? So this is just this is like basically sample data that I pulled together for another project. I took these points from the Census Bureau's gazetteer. A gazetteer is basically a directory of place names. And in this case, those points just represented different cities. And for the tests that I was doing, in some cases, I duplicated the cities and I put an attribute in here for a different name and date, just so we could see what could happen. But basically anything that any event or place, if you have coordinates for them, you can load them into a frame and plot them like this. So I think this still does require a little bit of explanation, like how do I know what coordinate reference system I'm supposed to use, and what are these numbers, and how can I look this stuff up? Let me bail out of the notebook and I'll give you a little bit of explanation, a little bit more explanation for the coordinate reference systems. So when we're talking about a coordinate reference system or a spatial reference system, the same thing. These are basically standards for modeling and locating objects on Earth that are based on geodesy, which is measuring and modeling the spherical Earth, and also cartography, which is the art and science for basically representing the Earth in 2 dimensions. And when we have these systems for these files, every system has at least 3 ingredients that make up the system. And then there's another family that has an extra 4th ingredient. All of the systems have something called a well-known identifier, basically a 4 to 6 digit number, which you will always use as input into your code to specify what the systems are. And the reason this is important is that if you have layers in a project and they're not in the same system, you can't interact with them. They basically don't correspond with one another. So if we tried plotting them on the same map, we could do it, but you would just get a really bizarre result because they are not really in the same system. So you want to put things in the same system, and you also want to choose a system that makes sense for the specific analysis that you're doing. And we'll talk a little bit more about that. So I mentioned that all systems have at least 3 ingredients. The first ingredient is that we have something that approximates the shape of the Earth. So the Earth is not flat, it's round, but it is not perfectly round like a beach ball. It's rather lumpy and uneven. So every one of these systems has an approximation of the Earth's shape that's either a sphere or an ellipse. That's the first ingredient. The second ingredient is something called a datum. So if we have the sphere or the ellipse and we have to line that up over the real Earth, how do we line that sphere up over the Earth so that things appear in the right place? Basically, there's a lot of math involved in doing that, and that math is called the datum, which is the very specific alignment of the sphere to the real Earth. And then the third ingredient is basically just a coordinate system, a grid that we slap down on the Earth so that we can locate things on it. You have those 3 ingredients, you have something called a geographic system, which you can use for representing the Earth in 3 dimensions. But of course, we're not looking at the Earth in 3 dimensions right now. Everything is flat and in 2 dimensions on our laptop. These systems don't have any instructions in them for flattening out the Earth, so they're all going to look exactly the same if we open them on our laptop. If we add a 4th ingredient, the 4th ingredient is a map projection, and a map projection is a specific set of instructions for flattening out the Earth in 2 dimensions. And there are thousands of different map projections. We have so many because there's no one perfect way of flattening out the Earth. If you imagine that you have an orange and you want to unpeel that orange, you can't unpeel it to form a perfect rectangle. It's just not possible. You're going to rip and stretch and tear it in different places. So map projections are essentially these distortions that we introduce to basically get the Earth in 2 dimensions. And you can only preserve one property of the Earth in a map projection. You can preserve direction or shape or area or distance, just one of those things, which is why we have so many map projections, because if you are doing a study where you have to calculate area, then you're going to want to use a projection that preserves area. Whereas if you're, making just a thematic map to display something, you might want to preserve like shape, for example. So there are different map projections that preserve different properties of the Earth. And then there are different map projections that are appropriate at different scales. So if you're making a map of the world, there are going to be a lot of different systems that you can choose from. Each one will look different and each one will preserve some property of the Earth. I just suggest if you're interested in getting a snapshot of what these look like, you can go to this radical cartography projection page, and they have a lot of nice illustrations for the different map projections. Once you zoom down from the global level and you start looking at continents or large countries, life gets a little simpler in that you can basically just choose a continent and you can choose the property that you want to preserve. So equidistant conic, these are the systems for North America, but there's an equivalent for every one of the continents and also for large countries. And we can preserve one that preserves distance, or that preserves shapes, or that preserves areas, so that you can choose the one that's appropriate for what you're doing. Zoom in even closer and things get even simpler. So we have systems that are designed for, in this case, for example, we have the example of mapping Rhode Island. So in the United States, there's something called the state plane system, where each state has like ideal map projections for that state. Little states like Rhode Island just have one system. Bigger states like New York are divided up into 4 different zones. And based on where you're making your map, you can basically just choose the system that basically captures the area that you're mapping. If you're not in the United States, there is something called the Universal Transverse Mercator, or UTM zones. These are basically bands that are about 6 degrees wide. And what you do is, I just look at the area that I'm mapping, and I look at a reference map and figure out what band it's in. And then I can set all my files so that it has the map projection of that specific band. So on this map, Rhode Island happens to fall in zone 19 north, for example. Or if I was mapping like the middle of Texas or all of Texas, I could choose like zone 14 north. And then there are a bunch of south zones for below the equator. So these systems are designed to basically orient the world around this specific zone. And while, again, you're not going to be able to preserve everything on the Earth properly, if you're looking in a very small area, basically the distortions for everything will be minimized. It's only once you start going beyond that area and measuring distances long outside of that that you're going to start to see things like errors in distance measurements. So in your case, these are just a couple of examples of if you're making maps, these are likely systems that you will use or encounter. I mentioned the geographic systems, which basically are just three-dimensional Earth. These systems are very popular for publishing coordinate data or as interchange formats that are kind of generic when you download data. It will probably be in one of these systems. Most coordinate data will be in WGS84. Stuff that the US government or Canadian government produces will be in NAD83. And then down here, these are examples of projected systems that basically are meant for 2 dimensions. And these are systems that don't use longitude or latitude, but they will have grids that are in meters or in feet. So pseudo Mercator, this is the most popular like web mapping projection. So this is what Google and Apple Maps use. The Robinson projection is a generic kind of global projection for making maps. I mentioned the systems for North America. And then if we were making maps of Rhode Island, we could choose the Rhode Island State Plain Zone, or we could choose the UTM zone that we're looking at. So basically you can make your choice, or if you don't know what to choose, when you download a bunch of data and bring it into your program, you'll pull up what all the coordinate reference systems are for the different layers. And then you basically just choose one and then convert all of your files so that they're in that same system so that you can work with them together. I know that's a lot to digest, but for folks who are approaching this, from this kind of data science perspective, I would say that, grappling with these like spatial reference systems is probably the #1 hurdle that you have to get over first. And even though there are thousands of these systems in your life, you will use like maybe 3 or 4, unless you're like an atlas designer or something like that, or you're just a real polymath. Yes.
Question, Chad. Is converting between systems lossless? Is there any error introduced from converting?
In some cases, so are there any errors introduced in when you're converting systems from one to the other? In some cases, there can be, particularly if you're moving between different datums. But if you're using modern systems, any loss would be pretty minor. It would only be if you're going back in time before we were using satellites to when people were doing this manually with telescopes and chains and then creating these systems that we'll start to see some possible errors. But for most modern applications and modern systems, no. So after my long-winded explanation there, let's go back into the notebook. So we have our files and now they're in the same system. Now that we have files in the same system, we can do stuff with it. So one example would be, we have these points and we have these polygons. Let's say we just simply wanted to sum the number of points that were inside every polygon. How could we do that? Within GIS and within GeoPandas, there's basically a construct called a spatial join. So in a regular database environment, if we wanted to join 2 things together, they have to have some identifier in common. But not in the geospatial world, because the thing that everything has in common is that they occupy the same space. So if we have these polygons of counties and these points, we can basically assign the attributes of all of the polygons to the point based on where the point falls. So for example, here, if we're going to create a new geodata frame, this S join is a spatial join. And we say we're going to take the points data frame and the county data frame, and these are the things that we're interested in taking along as attributes. We're going to do a left join, and the basis is going to be an intersection. So let me run this. And what that does is for every point, it assigns it the attributes of the county that the point intersects. And this statement here of intersects, this is defining how the spatial join is happening. Intersects is the most basic one. Any way the 2 shapes can interact with one another, you can use that as the basis of a spatial join. Do places touch? Is one enclosed within another? Do they overlap? Do they cross? Are they disjointed, in which there's no relationship at all? any kind of spatial relationship that you can think of, you can use that as a basis for a join. So if you don't have common attributes, you can basically use the fact that they're in space together. So this essentially assigns, like I said, every point the county that it falls within by using the spatial join function. And then now that I have the counties associated with the points, I can come down here and basically run, this is like basic Pandas stuff. This is an aggregate function where we're grouping by certain fields, and then we're aggregating and basically counting the number of those points that fell in every shape. And then I can get the summary table as the output. Another thing that you might want to do that's very common is if you download a lot of GPS data and you have points, you might want to stitch those points together into lines. And then maybe you're interested in calculating the distance of the lines. So an example of doing this would be like, for example, if I come back up to my points file a little bit higher here. So I have these points, but they're part of a group. And you can think of this as being like, if these were like individuals, every individual would have their own, basically the group would identify the individual. So that if this person is in these different places and moving from city to city, we want to basically draw a line that connects them. And then for person B, we're going to draw a separate set of lines for person B to connect the dots of where they traveled. So in GIS, this is just known as a points to line operation. And to do that here in GeoPandas, what we would do is basically we're doing a group by function. But instead of just grouping columns, we're going to group the geometry together. So if the points, you just have a pair of coordinates, we can group them together to basically serve as vertices where we can draw a line. So to do that, we say we're going to group the points, and we apply this function that basically just iterates through the points and basically creates lines out of them. We put those lines here into a geodata frame. And basically we're saying, just like we formed a geodata frame before, we say we're going to use these lines that we've created. The geometry is going to be the geometry of those aggregated points. We declare what the spatial reference system is going to be. And then once we have geometry, we have a number of other functions that we can apply, like this one, where if I have lines, I can calculate the length. If I have areas, I could calculate the area or the perimeter. So I can basically perform these operations just on the geometry so that I can get something that looks like this. In this case, the units that you're going to get out of this are the units that the map projection uses. So if I'm using the state plane system, that's going to be in feet. If I was using the UTM system, that would be in meters. Basically, if you go back up to where we ran the CRS command, it will tell you what units that system is in. And since I knew these are in feet, then I'm going to divide the length here by 5280 and get miles. And then just to show you that, that this actually worked, below here we have another plotting function, and this will let me draw all of these things on top of one another, my points, the lines that I created, and the polygons. In this case, instead of using like the generic plot function that comes with Pandas, here I'm calling on matplotlib. Matplotlib is a lot more complicated, but it allows you to really like have finite control over everything in your chart. If you notice, the other charts were kind of messy. The numbers on the axis all ran together. So I use matplotlib here basically so I could just rotate them. But then to create the map, I basically create my figure and my axis, and then I put one layer on top of the other. And then I can basically specify, these are the counties. So I can say I want to make the color white. I can change the outline to gray. For the points, I'll just make those black, and I can change the size of the marker. And then for the lines, if I want to display things differently on the map based on a category or a quantity, I can use this column function and say, hey, whatever is in this column, I want to use this as the basis for illustrating things on the map. So in this case, I'm just using the group ID for the lines, which gives each of my lines a different color. These were quantities, then we would get a shaded area map out of this instead. And then when we're all done, if you were like a GIS-y person, then you wanted to take these files and open them up in QGIS or something like that, we can just simply write everything to output. So down here, we specify where we want the files to go. And to output stuff, it's just this basically to-file function. And if I'm providing this, the geodata frame is the basis for the output, it's going to write all of the attributes and the geometry. And if I'm writing that to a shape file, then it just knows that I'm going to be writing a geospatial file out as the output. So if I run that, it will give me some nasty error messages. Shape files are really old, so you're not allowed to have more than 10 characters in the name of the column, which happens quite a lot. You can just ignore it. But that will create those output files. And then if I wanted to see what those look like, here in my output folder, here are the lines and the points that I created. I'm not a Google Colab user though, so can I download this folder really quickly? Let me come over here. I can copy, I can delete.
I've not actually tried.
That's all right. I've run this already and I have it somewhere here. So I'll just open up QGIS really quick and I'll open up files that I did previously. No, that's okay. I just thought of it now.
Well, QGIS loads. I have a question about the Rhode Island map.
Yes.
That big blob on the bottom. Yeah, what's that supposed to be?
Okay. So a question about what's up with this Rhode Island map with the big blob at the bottom. So these features came from the US Census Bureau's Tiger Line files, which is the Census Bureau's primary database for publishing all of the legal and statistical areas that they compile census data for. The Tiger files represent the actual boundaries, the legal boundaries that include land and water. So this giant blob is Block Island, and the water that is legally part of Block Island. So in using this as an example, using a boundary file like this is fine if you want to actually show the real boundaries. But if we wanted to show like land that actually showed us what the coast looked like and the fact that this was an island, we could use a different source. So there's the Census Bureau cartographic boundary files. The cartographic boundary files have been generalized to basically remove large bodies of coastal water and to show you actual land. But in this case, we're seeing the real legal boundaries that cover the land and the water. But when you're working with GIS data, that's a consideration, because if you're making a map, I wouldn't want to make a shaded area map using those boundaries. Nobody would be able to understand like what was going on because everything looks like blob-like. So here we are in QGIS, just to show you that it works. Let me go and find, I'm just struggling with like multiple windows open here at the same time. I just wanted to find the files that we just generated as part of that exercise, just to show you what it would look like if we were to take that output and open it up. If I can remember where I stored everything. New data, tutorials. This is basic Pandas, output files. So basically there are those files that we created in our notebook, just displayed within the GIS package. And actually, if we wanted to provide a little context, QGIS has the OpenStreetMap in here as a base map that I can just toss in here really quick. And now we can see where those things are. So in the work that I do, it's often, I want to be able to do things in GIS, but I don't always want to do a lot of point and click operations. So it's nice to be able to do stuff in Python, automate it, document everything that I'm doing. I get my output, and then I'll bring that output into QGIS, and maybe this is the place where I'll make like a nice looking final map with a scale bar and a legend and things like that, because this does a little bit better for like graphic design. Any questions about anything that we've kind of walked through here? Otherwise, I will mention that obviously the GeoPandas documentation is pretty good. So if you want to get a little mapping crash course, you can go to, you can basically search up the GeoPandas documentation. They have some nice tutorials and they illustrate how you can make a variety of different maps. This GIS at Brown guide, if you just do GIS at Brown, search it up, you'll get to this guide. This will provide you an overview of basically how GIS happens here at Brown, the different departments that offer courses, where you can find data, like some of the data sources that I mentioned here, and also links to tutorials, including this notebook, but also tutorials for learning desktop GIS if that's something that you're interested in. This is my penthouse suite on the 11th floor of the Sciences Library. Folks are welcome. On that GIS page is a link to my calendar. So you can basically book spots on my calendar and come talk to me about your projects or problems that you're having with your code or finding data or whatever it is. And I would be happy to meet with you. I also have hundreds of thousands of paper maps in this collection here. If you like maps, it's kind of a cool thing to look at. And you have my contact information here. And if you're interested at all in what we covered today, if you come to the talk next week, we'll go beyond this basic stuff. I'm going to demonstrate how you can use the Open Routing Service to basically chart network distances from origins to destinations using the Open Routing Service in GeoPandas. So we'll do that next week.
I look forward to it.
All right. Well, if there are any questions in the chat or let's see.
Oh, we have, this is great.
Oh, hi, Birkin. Birkin's my colleague in the library, so
Oh, great.
great. But yeah, that's the basis is how it works. And again, the #1 thing is figuring out the coordinate reference system business, which is a bit unfamiliar, but that's one of the reasons that we did this talk today. All right. Eat all this pizza before you leave. You're not allowed to go. So.